Hi everyone. In this video, we'll introduce another anti-differentiation method called trigonometric substitution. To motivate this topic, let's consider an example. This is an integral that you wouldn't be able to calculate with any of the methods you know so far, and you can pause and try it to convince yourself of that if necessary. But you might notice there's a difference of squares here and wonder if there's any way we can take advantage of that. The answer to that is yes, but we'll need to make use of this familiar trig identity, which you'll notice also represents a difference of squares. But how can we make use of a trig identity in an integral that doesn't have any trig in it? Well, notice the question we've been given has 1 minus x squared, and this is an identity for 1 minus sine squared. So if it turned out that x were the same thing as sine, or sine theta in other words, then this identity would be more clearly applicable. So let's pretend that x really is the same thing as sine of theta. And if you're wondering whether that's a valid assumption, I'll address that momentarily, but for now, let's just see where this train of thought takes us. If we now apply this trig identity, we could change 1 minus sine squared into cos squared, and this is great because now the square can cancel with the square root, leaving us with just the integral of cos theta. Well, technically plus or minus cos theta, but for reasons that I'll explain later, we don't actually need the plus or minus in this case. So you can see that the advantage of applying this identity is that it gave us a nice way of handling the square root, and that's nice and all, but something you shouldn't forget is that we haven't done anything with the dx. If I want to proceed any further, I need this to be d theta instead. So to figure out the relationship between dx and d theta, we need to go back to the substitution we made earlier. And we can just take the derivative on both sides to figure out what dx is equal to. The derivative of sine of theta is cos of theta, so this is our formula for dx. And next, we'll plug in this expression for dx in our integral. And that leaves us with a result which is still honestly pretty nice. This simplifies to the integral of cos squared of theta d theta, which is something we do know how to handle. Just use the even power method for sines and cosines that we talked about recently. You can check those details for yourself if you like, but the point is that there's something to this idea of substituting a trig function in place of x. The only remaining question is whether it's really a valid assumption to replace x by sine of theta. So let's talk about that. All right, so why are we allowed to take our x and suddenly just call it sine of theta instead? The reason is because theta is a new variable which we're allowed to define however we want. So for example, we're certainly allowed to define theta as arcsine of x. And if we did that, then what you'll notice is that if you applied sine to both sides, you'd get sine of theta equals sine of arcsine x, which after canceling inverse trig functions, shows us that sine of theta is equal to x. So in summary, replacing sine of theta by x really is a valid assumption as long as we define theta as arcsine of x. Here's another important question we need to address. Technically speaking, when we cancel a square with a square root, we always need to introduce a plus or minus sign. But in the example, I chose to ignore this. And the reason I can ignore it is actually because of the fact that theta is defined as arcsine of x. Now, what does that have to do with a plus or minus sign? Well, remember that arcsine is only capable of returning angles in quadrant 1 or 4 according to the definitions I gave in an earlier video. So then the cast rule tells me that when I take the cosine of an angle in quadrant 1 or 4, the result must be a positive number. And since we're only dealing with positive numbers, we're safe to ignore the plus or minus sign in this case. And for similar reasons, the same is going to be true in any other example where we use this method. So from this point forward, you can safely ignore any plus or minus signs that come up after performing a trig substitution. Now, in our motivating example, we made use of this particular trig identity because it closely matched the difference of squares that we saw in our integral. 1 minus sine squared was a close match for 1 minus x squared. And in general, it would be a close match for any difference of squares as long as it's of the form a squared minus u squared, where a is a constant and u is a variable. So anywhere you see a difference of squares of that form, the method we just used might be applicable. But then you might wonder, what if we had a sum of squares instead? That would actually be no problem because there's a similar trig identity that does resemble a sum of squares. So you might use this one, for example, if you saw an x squared plus 1 in your integral, or more generally, any sum of squares of the form u squared plus a squared. Also, we can rearrange this identity for tan squared plus 1 into an identity for secant squared minus 1. And you'll notice this would be useful if you ever had a difference of squares of the form u squared minus a squared rather than a squared minus u squared. With these three identities, we're really prepared to deal with sums and differences of squares of every possible form, and we'll practice that in just a moment. But if you haven't already, I suggest pausing here and writing these three identities on your formula sheet now. Okay, let's see if we can apply all these ideas to another example. Hopefully you notice right away that there's a sum of squares here. And with this new method, we have all the more reason to care about that. Now, if we want to try this new method, we need to look at these three identities and ask ourselves which one most closely resembles our sum of squares. Pause and think about it, and when you're ready to be spoiled, let's continue. I hope you correctly noticed this second identity is the one we need, since it's the only one that resembles a sum of squares. To use this identity, we're going to try making x squared plus 4 look like tan squared plus 1. Letting x become tan theta would be the first step in making that happen, because after all, if x were tan theta, then our integral would look as you see now. And that's a pretty good start, because we now have tan squared plus 4. But we want this to be tan squared plus 1, not plus 4. So how can we fix that problem? Well, we can always modify the substitution we're making so that it suits our needs more accurately. So in this case, we're going to say that x is equal to 2 tan theta, because if we do that, then this 2 is also going to get squared when we sub this in for x. And with that, we would see that both terms have a common factor of 4. So if we were to factor out that 4, then I'd be left with the tan squared plus 1 that I want. So let's factor that 4 all the way out front of our integral, just being mindful that it still needs to be under a square root. And after that, I'm left with the tan squared plus 1 that I wanted. So now I can apply the trig identity that I circled. By doing that, we've essentially turned our sum of squares into a perfect square, which allows us to cancel out the square root, getting rid of it entirely, and that's pretty awesome. Here again, you can ignore the plus or minus sign for similar reasons as what I explained before. Now, it's important that you don't forget that your dx really needs to be a d theta. So in order to figure out what dx is equal to, we need to take the derivative on both sides of our substitution, and after doing that, we'll have this formula for dx. So we can plug this into our integral, and then simplify by making a few cancellations. And the result of that is just the integral of secant of theta, d theta, which is about as good as it gets, because after all, this integral is literally on your formula sheet. So at this stage, you can just write down the answer, but we still need to express this answer in terms of x. There's actually more than one way to express this in terms of x, but I'll show you what I think is the best way to do it, and I'll request that you do it the same way in your own work. For starters, we need to look back to what is the relationship between x and theta in the first place. Notice that this relationship is equivalent to saying tan of theta equals x over 2. And with that, where we see tan of theta in our answer, we can literally just write x over 2 instead. So that would just leave the question of what secant theta is equal to if we want everything in terms of x. Well, in general, secant of theta is the reciprocal of cosine, Or in other words, it can be viewed as a hypotenuse over adjacent. And this, of course, refers to a right triangle containing theta as one of its angles. If we knew the sides of this triangle, then we would know the value of secant of theta. But we do know the sides because tan of theta can be viewed as opposite over adjacent. So that means the opposite side is x, and the adjacent side must be 2. After all, tan of theta is x over 2. The only unknown side now is the hypotenuse, but you can now use the Pythagorean theorem to get that immediately. Notice that the unknown side contains the same sum of squares that appeared in the original integral, which is a good thing. That's typically a sign that you're doing things correctly, and you can use that to check that you're on the right track. Now, using this triangle, we can form that ratio of hypotenuse over adjacent, and now that we know what secant theta is equal to, we can sub it into our answer, which is now fully in terms of x, so we're done. Something I hope you noticed about this example is that although trig substitution got the job done, it actually wasn't necessary to use that method at all. And that's because this integral resembles one which is already on your formula sheet. Pause and double check that this is the formula for inverse hyperbolic sine. So if you notice that, you could have just literally wrote down the answer without even doing any work. So take this as a good reason why you should commit all these formulas to memory as best you can, even though you've got them all written down somewhere. Imagine the amount of time you could save on your exam, for example, if you knew this formula off the top of your head rather than doing a trig substitution. And not just time, but also marks, because in a situation where a very inefficient method is being used for a simple problem, I might consider not awarding full marks. So take this advice to heart for the future. We can use trig substitution in really any situation where we see a sum or difference of squares, and it tends to be an effective and reliable method, but it's not a very efficient method. It's fairly technical and there's a lot of details that need checking. So for that reason, I would suggest that you use this only as a last resort, very much like what I suggested with partial fractions. But that's all for the basics of trig substitution, so look forward to the next video where we'll practice some more examples.